In this lecture, we're going to talk about the building blocks of this whole course, how to think algorithmically. And there are three facets to algorithmic thinking. There is maths, pseudocode, and flowcharts, or how a mathematician thinks, how a computer scientist thinks, and how an engineer thinks. These are kind of silly divides, but that's how we're going to look at these divides. So, the first thing we're going to look at is the flowchart. So, sorry, pseudocode. Now, in pseudocode, we use the operations that we spoke about before. It's just like maths, but you write it such that a computer can understand it. So you have addition, subtraction, multiplication, division, and modulus. Now, maybe the modulus, it might be the newest thing to you, and it's going to come up again and again and again in the future, but it's a nice one. So, what are the building blocks of the flowcharts? So each flowchart can have different parts of it. What do you input into the algorithm? That's our curved block. What process do we perform? Is there a decision that has to be made, and what is it? And then the end. You put that at start and end. It is the full stop at the sentence. Let's start with something very simple like adding numbers. In pseudocode, to add two numbers, a plus b, a is 5, b is 3, sum is equal to a plus b, and then you return sum. The reason why you have this return sum is the computer has to save the two numbers added together. It can't just, even your brain does that. There's a way that it remembers that there's two numbers added together and what is their value. The flowchart, you input A, you input B, 3 and 5. You do your operation, your process, and then you return the answer. So, it's much more elegant than maths, A plus B. There are going to be so many examples where we actually can't really write the algorithm as a simple mathematical formula, and that's why we need the other two. So here we have how a mathematician views it, how a computer scientist view it, and how an engineer will view it. If any of these three make most sense to you, that's the one you should focus on, because as soon as you get one of them, the other two will fall into place. They're all the same. It's just a slightly different way of writing about things. So, why do computers? And the answer to that is loops. Loops, 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 loops. What does mathematics and comedy have in common? Repetition. You just keep repeating again and again, a loop. So here is our simple summation loop. Add I to itself again and again and again. Yeah? Here we do it between the numbers 1 and 4. Here we do it between the numbers 0 and 4. But they're the same things. You just keep on repeating the operation. Now, a computer you can't just give it a list of numbers. What it does is, it adds 0 to 1, saves the answer. Then it adds 1 to 2, saves the answer. Then it adds 3 to 3, saves the answer. Then it adds 6 to 4, and saves the answer. And that's your answer is 10. But that's a loop, back down, back down, back down. So this is how we write it. We have to set up something called sum and say, okay, record your sum, remember this, and start at 0. And then we have our loop. We loop for I. So this for loop, you read it, for I in range 0 to 1. So that's I is equal to, starts with 0, then does 1, then does 2, then does 3, then does 4. Now, 0 to 5 is what it says there, but stops at 5. So it actually stops before 5. And so what it does is it just puts in the value, puts it in, puts it in, puts it in. And every single time it does it, it writes over the sum. So let's look at it in tabular form. The number of operations, how many times computer has to do something, is your left column. This will become more important later on. The middle column is the value of I, the right column is the value of the sum. So this is exactly what I said. So if sum is 0, then you add I to the sum, you get a new value of sum. You add that new value of I into it, put it in, you add them together, and so now we have our loop. Yeah? And that's what the computer does. And if we change this number to be 20, it'll do it 20 times, 100 times, yeah? So add up the numbers. And if we change this value I to be something else, it'll add together those values. But here's our flowchart form. Like before, we have to do the setup, tell it what sum should be at the very beginning and I should be at the very beginning. Then you tell it what the operation is. Sum is equal to sum plus I. Yeah? So sum is equal to sum plus I means it'll repeat the operation again and again and again. Yeah? But what it does is it adds a number to I and then goes here and goes. So if we go through it, I is equal to 0, sum is equal to sum plus 1. So that's 0 plus 0. I is equal to 1. 0 plus 1. That gives I is equal to 1. I is less than 5. Yes. If it's less than 5, you go back up. And you do it again. Then you do it again. You do it again. And you do it however many times until this is satisfied. Until I is bigger than 5, you stop and then you exit. And that is our for loop. So once again, we have how a mathematician would look at it, how computer science would look at it in pseudocode, and our flowchart. Yeah? The flowchart makes most sense. You see that? You go down and back up. That's repeat, repeat, until you make a decision. So there's more than one way of doing a loop. There's a for loop we just did. I'll talk about a while loop and then an if loop. All these are the same. They're doing the same thing. What it says is repeat until something. Do until something. So for a while loop, what we have is sum is equal to 0, I is equal to 0, and while I is less than 5, do everything in here and then return sum. So how do we think that as a flowchart? Set it up. We immediately hit our decision. If I is less than 5, then you go down and back up. And until it changes, you keep doing this loop around and around and around, and then you return your answer. Yeah? So here we have it, our while loop. The math's the same as the for loop because they're just the same thing. Then we have our pseudocode and we have our flowchart. All three are doing the same thing, but unlike with the for loop, you have a slightly different way of thinking of the hierarchy of it. The next most important decision statement is an if statement. So we've seen versions of this if statement before. This is what we have here. You have some value of x, some value of y. If x greater than y, you say yes, else you say no. So just decides left and right. But this can be more complicated because you can have else if, and all these different things. So this is how you build up the language of algorithms. There are loads of different logical arguments. Equals is equal to. So if two numbers are equal to each other, you make a decision. If they're not equal to each other, that's a decision process. That's important. Less than we know, greater than we know, greater than equal to, less than or equal to. There are basic logical arguments that we put in our decision. So in the live lecture, I'm going to go through these different examples of a simple loop, work our way through it, and talk about there. But the one that we're most interested in, so this is two loops added together. The most complicated one to think about is a double for loop. And we'll talk about this in the live lecture.